Hi everyone, in this video we will learn about an important result called the Green's theorem. And in order to talk about this Green's theorem, the first thing we need is a notion of orientation. So throughout this result we will be talking about a curve C, a closed curve C in space, and a region enclosed by this curve, which we will denote by the region D, or by the letter D. And we refer to this positive orientation as a counterclockwise traversal, or another way to think about it, which is actually more general, is that the region D is always to the left as you walk along the curve C. So that's another way of thinking about a counterclockwise motion, but this is more general because we will see that there's a special case where a counterclockwise may not be positive because it's not on the left. So as you walk along this curve, so for example of a positive orientation would be, you basically have to decide, all right, which way do I need to walk so that the region is always to my left, and that would be this way. So if you imagine walking over here, then this is always to your left. Whereas an example of a negative orientation would be if you are walking in this direction, and this is to the right. The left is on the outside. So this would be called a negative orientation. And the Green's theorem is essentially a counterpart or reformulation of the fundamental theorem of calculus, which tells us that derivatives and integrals are inverses of each other. And the idea here is, if we have C, a curve which is positively oriented, which means that the region it encloses D is to its left, it's piecewise smooth, simple closed curve in the plane, and D is the region bounded by C. If P and Q have continuous partial derivatives on the open region that contains D, then this line integral given by P dx plus Q dy is the same as the double integral of the difference between these two quantities, which recall conservative potential fields. Conservative fields have this to be 0, right? So we come back to this expression. And how is this similar or a counterpart to the fundamental theorem of calculus is, if you look at the right hand side, there are two integrals and one derivative, and on the left hand side you have one integral. So you can kind of think of it as fundamental theorem where one of the integrals is cancelled or undone by the derivative. So let's look at an example. Now, since this is a theorem, that is, it's a result which helps us, find line integrals in scenarios where it may not be straightforward. It is not that you have to always use it, but that in some cases it might be easier to use. For example, evaluating this line integral where C is the triangular curve consisting of the line segments from these three given regions, it doesn't mean that you have to use Green's theorem, because of course we already know how to evaluate line integrals, and we can use those methods. But let's look at an example from the line segment from 0, 0 to 1, 0, from 1, 0 to, oh wait, this is a mess. Sorry, let me fix this. To 1, 0 and 1, 0 to 0, 1. So we have a 0, 0, 1, 0, a 0, 1. So it goes from 0, 0 to 1, 0. So that establishes the direction. It goes from 1, 0 to 0, 1, and then down. So this, if you look at the region that it bounds, the region is to the left of, if you're walking on the boundary, which means it is positively oriented. So you can evaluate the line integral directly, but you could also go and use the Green's theorem here, making it the double integral over the region del q over del x minus del p over del y dA. And here, this, remember, is the function p, and this is the function q, so that del p over del x is del p over del y is 0, and del q over del x is just y, which means our double integral is a very simple double integral, dy dx. And where does y go from? Well, if you look at the direction for y, you can find the equation of this line is 1 minus x. It's a slope of -1 and intercept of 1. So this goes from 0 to 1 minus x, and x goes from 0 to 1. So that makes it a very simple integral to deal with. 1 minus x squared 1/2, 0 to 1 dx, which then becomes 1/2, and a 1 minus x cubed divided by -3 from 0 to 1, so -1/6. Plugging in 1 gives you 0, and 0 minus 1 cubed. Negatives cancel out, and you get a positive 1/6. Again, you do not have to use Green's theorem, but as you can see, applying the Green's theorem makes this expression, the del q over del x minus del p over del y, very simple. It's just y. Let's look at another example. Evaluate this line integral where c is the circle x squared plus y squared equals 9. Now here is a scenario where just by looking at the problem, you can probably infer that maybe I want to use Green's theorem, specifically because the integral here does not look very nice, right? So you have e raised to sine x's, you have all these complicated square roots, which maybe you don't want to deal with. And there's the fact that it's a circle, so going into double integral, maybe we can use polar coordinate, which becomes easier. Okay, so the conditions are satisfied. So by Green's theorem, we'll have del q over del x. So that's q here. You can see that this complicated square root y to the 4 doesn't have any x term, so that this derivative is simply 7. And del p over del y, again, this is p. The e raised to sine x doesn't have a y term, so these just come out to be constants. So that this is actually just 4 dA. And you can do this in multiple ways now, because this is 4 1 dA, and when we have a double integral of 1, then that's just the area, which in this case is the area of a circle of radius 3. So this is 4 times pi r squared by 3 squared, which gives 36 pi. You could convert this into polar coordinates, r dr d theta, put the limits 0 to 3, 0 to 2 pi, we'll get the same result. You could also do what we did here, which is recall that the double integral over a region D of 1, or just a constant, is just the area of that region. In this case, the region is familiar to us. It's a circle, and we know that area of a circle is pi r squared, so we can use that directly to get our result. Okay, so that brings us to the next idea, which is, well, we were lucky that that's what we got in the previous example, or is there something more that can be done with it? And it turns out that there is, because if you think about the double integral of del q over del x minus del p over del y, if we can make that to be equal to 1, then we can get the area, right? So using this as an area, we can, so if we choose P and Q such that del Q over del X minus del P over del Y equals 1, we can use the Green's theorem to find area. And what we mean by that is, by using the Green's theorem in the reverse, we can create a line integral which then can be used to find the area. So there's a bunch of different possible choices you can have for Q and P, right? So for example, if I choose my Pxy to be 0, right, then this is 0. And if I choose my Qxy to be x, then we have x prime minus 0, which is 1. So that works. We can also choose Pxy to be negative y and q to be 0, because then you have 0 minus negative y prime, which is also 1. Or you could choose, somewhat complicated stuff, like Pxy is negative half y and Qxy is half. So then this becomes, when you take the first derivative, 1/2 minus negative 1/2, which is 1. So that the area, now using the Green's theorem in reverse, which would be double integral of 1 dA, by Green's theorem in this case can be written as the line integral of x dy, if we are using this, right? So a, which would be the same as the negative line integral of y dx if we are using b, which would also be 1/2 line integral x dy minus y dx if we were using c. And these are not the only choices. You can make other clever choices for p and q. It's just that these are the simplest ones. Let's look at an example. Find the area of the ellipse x squared over a squared plus y squared over b squared equals 1. You have done this in several other calculus courses using different ways of working with it. So we will use a c here, which is that it will be 1/2 line integral of x dy minus y dx. The parametrization of an ellipse parametrization is similar to a circle, the only difference being the coefficient a and b are different. If they are same, then they would be r, which is why special form of ellipse where a equals b equals r is a circle. So we have that, which means we're making one full circle. X is a cosine t, dy is b cosine. This should be sine, sorry. So derivative is b cosine t, so this would be b cosine t dt, minus y is b sine t, and the derivative is negative a sine t dt. And as you might be expecting, what's going to happen is the good old cosine squared plus sine squared, which is 1. So giving us ab over 2, and then a 2 pi from the integral, giving you pi times a times b, which is the area of an ellipse. And once again, if a equals b equals r, then we have a circle, and the area is pi r squared. There are some extended versions of the Green's theorem, which we will not be, we will be using it sparingly, but the idea for the extended version is, what if we have a region which has to be constructed from union of, to be more specific, finite union of simple regions. So for example, suppose we have a C1 curve here and then a C3 curve going up, and we have a negative C3 going down and then a C2 here, giving us two of these regions, calling them D1 and D2 then the line integral C1 union C2, which we've seen in the unit of line integral, that can be done. You can just add up all the line integrals when you take the union, is going to be C1 union C3. So C1 union C3 becomes one closed curve, will correspond to the double integral on the closed region D1, and the line integral C2 union negative C3 that encloses the region D2 will equal D2 in the Green's theorem. What this does is it also helps us now evaluate or apply the Green's theorem to regions that have holes in them, which we will see in the next example. Suppose we are to evaluate this line integral where C is the boundary of the semi-annular region and D is of the upper half plane between x squared plus y squared equals 1 and x squared plus y squared equals 4. So an annular region is something like that. So you have x squared plus y squared equals 4, and you have x squared plus y squared equals 1, but just the top half. And you have this kind of walk going on here. And since p is y squared, we have del p over del y is 2y, and q is 3xy, del q over del x is 3y. So the double integral becomes 3y minus 2y, which is just y dA. And again, a circular area means, or region means, I can write this in polar form, going from 1 to 2 and 0 to pi, which then becomes 0 to pi sine theta d theta and 1 to 2 r squared dr, the first of which gives you 1, and the second one is going to give you a 1/3, 8 minus 1, which is 7. Sorry, this is going to give you a 2 because you'll end up with cosine a negative 1 minus a negative 1, giving you negative 2 times a positive 2. There's also a further extension. You can apply Green's theorem to regions with holes in them. What you do is you're going to break this down into a top half path and a bottom half path, and this is where the counterclockwise way of looking at positive orientation fails, and that's why you have to stick to the left orientation. As you walk here, this is a clockwise motion, as you can see, but this is a positive orientation because the region is to the left. Okay, let's look at one last problem. If you are given a vector field given by negative y I cap plus xj cap over x squared plus y squared, show that the line integral equals 2 pi for every positively oriented simple closed path that encloses the origin. So first of all, this question is different from any we've done so far because it's asking us to show something for every, right? Which means it's kind of like a proof. It is not theoretically possible for us to check for every single curve because there's infinitely many. So there must be some other way in which we can work with this problem. For every positively oriented simple closed path that encloses the origin. So which means we have to start with any arbitrary path. The only thing that it satisfies is that it encloses the origin. So what we do is, let this be C, and let us consider a counterclockwise oriented circle, C prime. So let's take a shape that we are familiar with, which is a proper circle of radius A that is small enough so that this curve C prime is entirely inside of C. By doing this, now we have created this particular region between the two circles. And we will see what we can do with that. So if you look at C, union C prime is positively oriented. C prime is not positive. C union negative C prime is positively oriented. So we have the result, which tells us that the line integral p dx plus q dy plus the line integral along negative C prime of p dx plus q dy is the double integral of del q over del x minus del p over del y dA. Which is what? P is y over x squared plus y squared, right? So P is x squared plus y squared. So del P over del y, we're going to have to use the quotient rule. We get x squared plus y squared whole squared. Derivative of the top, which is with respect to y is 0. So it's just derivative of the bottom, which is to y, and q, which is negative y over x squared plus y squared. Del q over del x is again x squared plus y squared whole squared. Derivative of top is 0, and then the bottom is y and a 2x. Oh, there's a problem here. Okay, I got this wrong. Sorry. P is the x, the first part. P is actually negative y over x squared plus y squared. So that when you do this, you have x squared plus y squared whole square, derivative of the top. So you have negative 1 times x squared plus y squared minus derivative of the bottom, which is 2y times negative y, so plus y squared, which makes it y squared minus x squared over x squared plus y squared whole squared. And x is x over x squared plus y squared, del q over del x, quotient rule again, x squared plus y squared whole squared. Derivative of the top is, with respect to x is 1, so you get 1 times x squared plus y squared minus x times 2x, which is 2x squared. So you get y squared minus x squared over x squared plus y squared whole squared. These are the same. Because these are the same, it means del q over del x minus del p over del y is 0. So you have that the line integral of p dx plus q dy for this case plus the line integral along negative c prime of p dx plus q dy equals 0. But for line integrals, we know that changing the orientation only makes it negative in value. So this is going to equal the line integral dx plus q dy. And what does that mean? By Green's theorem, or sorry, you don't need Green's theorem here. This is just rewriting the line integral in vector form. This means that this and this are the same. So the line integral along C and C prime are the same. But C prime is just a circle with radius A, which we can find. And this is just 0 to 2 pi f of rt in vector notation times r prime t dt, which is 0 to 2 pi. So you plug in the values, you get negative a sine t plus a cosine t divided by x squared plus y squared, which is a squared cosine squared t plus a squared sine squared t dt. And what happens is, again, the same story. At the top and the bottom, cosine squared t plus sine squared t is 1. And again, sine squared t plus cosine squared t is 1. And a squared cancel out, so you are left with 1 dt, which is 2 pi. And so what we have shown is, starting with an arbitrary curve c, the line integral is the same for any curve c as the line integral about c prime, where c prime is a circle with radius a. And then we saw that when you find the line integral along c prime with a circle of radius a, it is just equal to 2 pi. So they're all equal to 2 pi, which is what the problem asks us to do. Now, if you recall, what it means to be a conservative field was that it's path independent for line integrals, and that this equals 0, which happens for a closed simple loop C. And you remember the condition for that was this equals this, and when that happens, del q over del x minus del p over del y is 0, which then gives you this path independence, which is part of the reason why the above result was 2 pi irrespective of the path c prime that was taken. So that brings us to an end for Green's theorem. There are other theorems that we will be covering in this class, which are also closely related to Green's theorem. But that's it for this particular video. Thanks, everyone.